Hello everyone, welcome back to the channel, and welcome to my special tapped horn design video I've been intending to make for way too long now and haven't gotten around to. Now before we get into all this stuff on the screen you see right now, basically Hornresp and everything that goes with it, and these two giant tapped horns I've got in the background here, I just wanted to mention in my last video on tapped horns, I mentioned that there was a possibility of me doing a second or another project like this featuring 4 5-inch drivers. Well, we're going to talk about that one, but unfortunately, time being what it is, I no longer have the amount of free time I would require to do that kind of a project and still make regular video content. So it's basically spend the next 6 months doing another tapped horn video, just one video, or doing a regular video every Saturday on cassette decks and other electronics and that kind of thing. So I thought maybe the best compromise was to do this video and sort of talk about my design process for tapped horns and how I go about it. Now before we get into all the good stuff here, I wanted to mention I do not claim to be the end-all be-all of knowledge on this subject. That would be Tom Danley. I am not Tom Danley. I'm just a guy who wanted to learn this stuff and kind of broke my brain a little bit trying to figure it all out back in the day. Started doing my first design when I was, let's see, when was that now? That was 2009. And then I did it again in 2010 for this giant beastie on the bottom here you see in the shot. But yeah, I'm not perfect. Take everything I say with a grain of salt. Maybe you know a better way of doing things that I don't. Maybe you've got questions after this video that I haven't answered. If so, drop a question in the comments and I'll see if I can answer them. So, let's get into this here. I'm going to dismiss Hornresp for now so you can see the image on the screen, and I've got a little cheat sheet here with outline sheet with all I wanted to talk about today. Gonna be a lot of info dumping. Sorry about this. It's the only way to do it. Okay, the first thing we want to do when we figure out what we want to do with a tapped horn is figure out our objectives. Do we want to do this for pro audio? Home theater? How loud do we want it to get? And what kind of bandwidth are we looking for? So for me, these two designs you see on the screen here, let me move this down a bit. These two designs are obviously for home theater. So basically, the intention here was to design around what Dolby reference level is, which is 115 decibels plus 5 or 6 decibels on top of that to account for headroom. So basically, what I wanted to do was build a couple of awesome subwoofers that were really efficient so I wouldn't have to buy much amplifier back when I was still on welfare. And I wanted it to be able to do 115 plus 6 decibels at my listening position, which is 11 feet away from my screen and about 12 feet away from these subwoofers. So yeah, that's actually quite a challenge when you consider my room, which is, as you can see here, it's just wood paneling, and behind that wood paneling is concrete. So we've got concrete, and then on the floor we've got even more concrete. And what's worse is the basement is open to the rest of the house, so there's basically no pressure vessel gain whatsoever in this room. So that equates to a lot of SPL being needed for me in order to get to Dolby reference level at my listening position. So the only way to do that was either to build something extremely efficient or build something less efficient that required a ton of amplifier power and a ton of money. So basically what I tried first was I tried to build an 18-inch Mach 5 audio IXL in an 11 Hz tuned enclosure. And it kind of worked, but it wouldn't hit SPL levels at listening position. It got to maybe 113 at best. And that was it running flat out with 600 watts. So I wanted to take that same 600 watts, or actually originally I wanted to do half that number, 300 watts, through this top subwoofer here and get all of my SPL I needed at listening position. And as it turned out, the one was just barely enough to do it. So yeah, Anyhow, what are the advantages of tapped horns? Well, efficiency, affordability, and they use both sides of the dryer diaphragm in a horn alignment. And yeah, that's basically it. Efficiency. Now, there are disadvantages, of course. One of those big disadvantages being there's a tipping point in terms of size versus efficiency. There comes a point at which you can tune these so low that the size becomes so great that they lose their advantages against a vented box, like basically your usual ported bass reflex design. That's basically my goal for these, is I want them to put maybe 6 decibels on top of a vented design. Anyhow, there's other disadvantages like sound quality. These are never going to be as good sounding as vented boxes or ported or sealed boxes. It's just how they are. Because you've got this long pathway here for the sound to go through. In this box, it goes from here, down to here, down to here, down to here, here, up here, and then finally out this side. That's a lot of path length to go through for the sound waves to come out. So you find what you get is, because there's all these hard surfaces in here, you get ringing. And there's no way around it in a horn, or in a bass horn. Basically, the sound just sort of bounces around in there until it sort of dies out. And both of my designs have this. And you have to choose whether or not you can live with it. Personally, I can. But, yeah, these are not designs I would really advocate for being audiophile grade. I'm not sure I would put them there. There are ways you can get them to sound better and worse and whatnot, but I'll try and talk about those as this video goes along. It's probably going to be a long one, so sorry about that. Can't get around it. Okay, so I talked a little bit about my general goals with tapped horns. Like I said, 6 decibels more than a vented design with the same drivers. But everything's about compromise when it comes to these things. So the general compromise is low, loud, little. You can pick any two, and you have to compromise the third. In this case, as you can see, I compromised the little part of it, because these are enormous. I mean, both of them are enormous. But another thing you have to really consider is how big the room is going to be when you design these things. Is it going to be like enormous cathedral size room, or is it going to be just a small space? Mine's kind of a small space, so I can get away with these 2 horns I've got here, but maybe you've got a gigantic cathedral ceiling living room open to the rest of the house, and your horns are going to be trying to fill like 4,500 square feet of space or something like that. And you're sitting 20 feet away. What do you do then? Well, then you've got to up the SPL for your design. These two, the drivers they use in I used in these, sorry, they both have the cone surface area of 10-inch drivers. That's not going to be enough if you have a gigantic room, but it's plenty fine for what I've got going on here. And you could argue that with a gigantic room, all you've got to do is build more than one of these, kind of like I have here. Anyhow, yeah, when it comes to bigger rooms, you have to kind of factor that in for your design. Sometimes you can't get below 20 hertz with a room that's enormous. That's why the Danley Cinemonster, the TH221, is tuned to only like 20 to 22 hertz. It has to fill enormous rooms, and that requires enormous SPL. So yeah, it's all about compromise. Now, driver considerations. Let me go to a different screen here. I'm going to go to this screen here. This is the very first tapped horn driver I decided to actually design and implement. So, what do we want in a tapped horn driver? Well, the quick and dirty method for me is I look for a QES of around 0.33. And with this driver here, it's a weird oddball driver, 8 by 12 inch, like I said, got the surface area of maybe 10 or 11 inches. But if we go down here and look at the QES, it's 0.36, which is just about perfect. In fact, it is kind of perfect. The little bit it's off by just does not matter. But that's just the quick and dirty method. There is a formula you can use to ideally determine whether or not a driver is good enough. What you want to do, and I got to credit my friend Mike for coming up with this. I don't know if he wants me to give out his last name, but it's his formula, so, and he knows way more about this stuff than I do, so I wanted to give him a little bit of credit. So the formula is BL squared. Let's see, where's our BL here? 14.57 times 14.57. Okay, now we take this number, divide it by RE. Let's see, where's our RE on this one? It's right in front of my face, I just know it. Oh, there it is, 3.2. And now we want to divide it by SD, which is 460. And that gives us a number of 0.14. Now for an ideal tapped horn driver, you want 0.12 to 0.20. Below 0.12 to about 0.08, that's ideal for a folded horn. Little less magnet strength on those. So you need a little bit more magnet strength to do a tapped horn. So that's basically what you're checking for with the formula. Now it is possible to have too much magnet with these things, but I find that most drivers do fairly well, as long as it's not too far off of 0.20. So anyhow, there are some other considerations we have to look for when it comes to a tapped horn driver. One, believe it or not, is not X-Max. I know you're thinking X-Max is really important and stuff, and it is important for most driver designs, or most subwoofer designs, rather. But for tapped horn designs, the more important value is X-Mech, or mechanical extrusion. X-Max really doesn't matter. You want to know exactly where the driver is going to start clanking, so you know exactly what to model in Hornresp. And unfortunately, I didn't have that number when I put this thing into Hornresp for the first time, so I kind of had to just wing it here and just go off of X-Max and just hope I was building something I would be able to live with. But I will tell you this particular driver, because of the magnet it uses, you can't bottom this thing out. I've put 1100 watts into this top horn here, and it took it. It didn't clank once. So that's pretty cool. Now that is not the same way for basically this one. This is the driver I picked for my second tapped horn. Rather, this is the new version of it. We'll talk about that in a minute or 5 or 10 or whatever, because there are some differences to this new driver compared to what I actually built for myself. And if you can believe it, this one's actually more ideal for a tapped horn than my original driver was. So, yeah, let me get back to my outline here and we'll start talking about the original tapped horn first I designed. So what were my goals with this tapped horn? Basically, I knew I was going to be using 2 of these. And what I wanted was 16 Hertz extension at Dolby reference level, at my listening position, so basically 120 decibels, with 350 watts. That is a gigantic undertaking, I'll tell you right now. That's why it takes you 6 months to do one of these designs, or it takes me 6 months. Maybe it takes you longer or less, I don't know. Anyhow, basically what I knew was, if I can even talk right now, basically what I knew was I was going to have corner loading going on, so basically 1/8 space loading, which helps a lot with these things. So yeah, I just kind of hoped it would do it. And let me get to Hornresp now, because we need to start getting into that now. Okay, this is the design right here. This is my original tapped horn. This is the top one. So let me do that. So this is the design right here. Basically what I did to come up with this design was I started plugging numbers into Hornresp here and just sort of winged it from there. There's a wizard you can use here. I don't know if I can get to it without editing my design here. There's this loudspeaker wizard. And I basically used this. I played around with all these sliders until I came up with something I thought was going to work. I came up with the ideal horn length based on calculations I did before coming into here. Like, it's a quarter length resonator. So basically it was, I calculated the wavelength of a 16 hertz sine wave. I went 1/4 with that and just sort of came in here with that. So that's how that worked. Now, in terms of this design, as you can see, it's set for 2 pi right now, which is half space. Basically, not a realistic scenario for any room. So I'm going to go into eighth space here, like I have it in my room here, just like it is right here. You can see it's firing right into that corner. So I'm going to set it for that as we go along here. So how does this model out? Well, I'm going to hit the calculate here and we're going to talk about this. So this is basically what the horn models out to at full power before it, well, I shouldn't say full power. This design is actually excursion limited, not power limited. Or it actually theoretically would be if I could ever get the drivers to clank. But yeah, this is basically what I thought I was getting in for when I designed this. As you can see here, 17.72 hertz. We've got 126.4 decibels at 1 meter. And I'll tell you right now, it measures out that way in reality. I can peg a 127 decibel SPL meter with this horn. Just sitting on the floor, it does it. And it vibrates the concrete floor doing it, which is crazy, but that's beyond what we're talking about here. So this is basically what you kind of want for a tapped horn design, what it kind of looks like in Hornresp here after you get it done. Basically what you want is you want a straight line going from here to every peak, and you want the same straight line coming down here on every dip. So basically you're trending upwards as you go up in the pass band. And as you can see, the pass band ends at roughly 16.5 hertz on this design. This is the design as built. It's not the design as originally modeled. We'll talk about that later too, because that's part of the whole folding nightmare you got to go through with one of these. But anyhow, you just want this straight vertical line, or slanty line going up through the pass band. And that's how you get it to look ideal. Anyhow, this is just acoustical power. What we got to get into here is some of the more difficult parts of this, and I hope I can explain this. Okay, so this is the schematic diagram. We've got a 657 liter design, or 658 if you will. Basically, you've got the throat here and the mouth here. And this is where the driver is. As you can see, that's where the tap is. So basically when you fold these, you have to make sure that this comes up over here inside the design, and I'll try and explain that better later. Anyhow, let's go to acoustical impedance. This is important. Basically what you want is your acoustic impedance and an acoustic reactance to cancel each other out. So you want these red peaks, or these red dips, and these black peaks to be roughly equal and right aligned over top of each other, if that makes any sense, kind of like the way it is here. And the lower the peaks, the better. Now this isn't, like I said, the original modeling. The original model looks a bit different than this, because when you go through the process of folding these horns, you have to constantly come back into Hornresp and remodel your design based on measurements from the fold. And if you get results that you're not happy with, you've got to go and fold it again. That's why it takes 6 months. Anyhow, let's see here. What else? Electrical impedance. I usually don't pay attention to this. Diaphragm displacement. This is extremely important. Basically, what I did here was I tried to keep it under X max, which is right here inside the passband. Now, you can see down here, it's at 12.09 millimeters. That's plenty fine for those drivers. Like I said, their X max is 12 millimeters, and X mech is going to be above that always. So this is basically my limitation on my home theater subwoofer designs. Does it stay inside mechanical X max or mechanical excursion within the passband at my desired volume levels? And this one does. However, you'll have noticed it goes way off the chart over here. And this is another big limitation of tapped horn designs. You have to aggressively, and I do mean aggressively, high pass them. Otherwise, your driver will be bottoming out as soon as it unloads, which is right below tuning frequency, which in this case is 16.26 hertz. So yeah, watch it. You've got to high pass them. It's critical that you do so. It doesn't matter which tapped horn design you buy. If you get one commercially, you have to do this. Always. It's every bit as important as low passing it. And we'll talk about low passing later. Let's get into phase response. Now, this looks a little squirrely at first, but that's because this version of Hornresp does things a little different from the way I've gotten used to it. Basically, what we want to do is go into the delay here, hit the default button, and then go OK. Now, once you do this, what you need here is you want the phase response to be within 90 degrees within your passband. So our passband is roughly 16.5 hertz, so right there. And it looks like we're good all the way up to maybe 190 hertz. And you might be tempted to say, oh, that's great, you've got 3 octaves there. Well, yes and no. What you find is that, let me go back to, not that one, this one. You find that it gets really peaky and dippy above 2 octaves or so. Now, maybe you can live with that, maybe you can't. That's up to you to decide. But in this case, I find that high passing below 80 hertz is just fine for this design. It does not mind that one bit. Now, as for group delay, I never do anything in here either, so we'll go back to the input parameters here first. Or next, as it were. Now, each of these fields are important, and you can calculate some of them within Hornresp. Like for CMS, you can double-click, and then it asks you if this is correct, and you say yes or no. In this case, it is. So we put our VAS in here, whatever it happens to be, and then it'll calculate CMS. And I've already done that, so I'm not going to complete that. But many of these fields can be done like that. So yeah, this stuff down here, this is for rear chamber volume. This is basically if you want to do a compression chamber or something like that, or something really weird with it. But we're doing tapped horns today, so we don't have to deal with it. Now over here, we can select what driver alignment we're doing. If we double click, we can choose how many drivers in series or parallel we've got here, and in what configuration. And yeah, that's basically what that does. Now, one very critical parameter we need to pay attention to in here, when it comes up when you mouse over the SD. Now you'll see down there on the bottom of the Hornresp display there, it says SD driver diaphragm piston area, 2 times SD over S2 compression ratio. That is critical. That is very critical. If you use the compression ratio too high, you will destroy your drivers. And I I must confess I've not yet been able to determine exactly what a safe value is here, so I tend to play very conservative. I try to stay around 3-to-1 for most drivers. It's very likely safe for all of these drivers to do well over 3-to-1, like 5-to-1 or 6-to-1. I've just never tried to do it because I don't like tearing apart my drivers and having to buy new ones. So that's basically what I do there, is I just err on the side of caution. Now, there is a compromise there. If you err on the side of caution and you have a compression ratio that's too low, suddenly your enclosure becomes much bigger than it needs to be. So, like I said, there is a trade-off. There's always trade-offs. So yeah. Let's see here. Do I want to do anything more with this? Yeah, there's a lot more you can get into with this software. Basically, it can model just about any alignment of subwoofer you want, whether it be vented boxes or sealed boxes or tapped horns or tapered quarter wave pipes or whatever. Transmission lines, you name it, this thing can do it. So what I want to do right now... No, I will not save changes. I will go to the other one. The one I did as... Oh, let's see, is my... Can I do it better? Proof of concept. The SDX horn. Let's see, where is it here? Fold 3L. And yeah, you can see just how many times I had to refold this in order to get it looking good. There's fold 3, 3B, 3C, 3D. There's another 3D, 3E, 3E based off of a spreadsheet we're going to have to talk about in a minute. 3F, 3G, 3H, I, J, K, L. And L is what I ended up going with. This is the final product. So, before we go any further, this is the original XDX10. This is not the one you can buy today. So keep that in mind. Now, as you can see, the compression ratio is still about the same, 3-to-1, because I wanted to make sure I didn't tear apart my drivers. Right now it's modeled in 2pi, so let me get that back down to what I'm actually dealing with in room, and I will reorient that to the design we're actually talking about now. And you can see what I've got in here for power. This is 350 watts. Again, excursion limited. Now, if you use the new version, well, actually, we'll talk about that later. I don't want to get you too far into the weeds here. So basically, here's what I've got with this one, with 350 watts. So basically, 126, 127 decibels at 1 meter. Corner loaded, and it's basically a little bit compromised here. You can see it's not quite the slanty line you really want to get from these. It's more of a horizontal line, and this is because the horn flare is compromised in this one. And the reason the horn flare is compromised in this one is because I had to get this design within 3 sheets of plywood and no more than that, because plywood was and still is expensive. So that was the compromise I did with this one. A slightly bigger horn flare would give you a much better looking response there. But anyway, like I said, this is the final folded result, so this is what we're talking about here. Let's go back into acoustical impedance, and you can see I got it looking even better than the Tang band horn, which is up here, the original one. The peaks and dips are much lower on this one. And this is basically because I refolded it about 1,000 times to get it this tame. So anyhow, we'll go into phase response again. We've got this same stuff going on here. We got to do the thing with the delay again. And as you can see, once more, we are within 90 degrees in the passband. So that's good. Now, diaphragm displacement. This is very important with an SDX driver because of the sorry about that. Because of the XBL squared motor design. These clank a lot easier. And this is basically what I've got here. This is what I concluded was actually safe for the design. I think X max back then was something like 18 millimeters. So I sort of gambled on 21 millimeters or so being safe for the driver. And it's very safe for the current driver, but that's neither here nor there. But this is basically what I've got. It's quite safe to run this at 350 watts as modeled. And you can see the center frequency is about 16.26 hertz again. Because I basically went off the same calculation for horn length as I did for my tang band horn up there. But as you can see, once again, excursion goes out of control below the pass band. You've got a high pass, big time. Use 48 decibels per octave at 14.5 hertz with this design, and you can feed it all the power you want, pretty much, until it starts clanking above 20 hertz here. That is. I think 600 watts is safe for it. 5 or 600, something like that. I can't remember. Anyhow, let's go back to input, parameters, and yeah, that's basically the SDX horn here. Now, is there an easy way to start off with this Hornresp stuff? Is there a sort of a shortcut you can use to sort of get you started in this program? Well, yes, there is, and I didn't get that ready. Okay, so this is how I start off with Hornresp these days. Basically, it's a time saver. You don't have to go into the loudspeaker wizard and just sort of tweak all the little parameters the way I did for my first tapped horn anymore. And this is because a really awesome guy who goes by Soho54 at AVS Forums, much credit to him, this is a massive, massive time saver. This is basically the shortcut. Basically what you do is you take your input parameters for your drivers, the ones you decide to go with. Basically you pick your drivers ideal for a tapped horn and plug it into this spreadsheet here. And then you go through all these parameters. You select your, oh, let's see, where is it? You got your number of drivers there. Right now I've got the Sundown 15-inch ZV3 in here. We're going to talk about that driver real soon, because this is Wolfhorn San Andreas we're looking at right here. And oh, wait till I tell you guys about this design. But I'm getting ahead of myself. So this is where you input your horn flare, or your horn diameters. You basically put in your desired horn flare, and 0.55 is the lowest I will go. 0.5 is just a little bit too compromised. Remember, the bigger the horn flare, the more enclosure volume you're looking at, so there's always a compromise there. So you put in here your desired low corner, which is the knee or the 3 decibel down point. In this particular horn, it's 14 hertz. Yeah, we're going to talk about this design later. You mark my words, we're going to talk about it. And you put in your high frequency cutoff here. Not really that necessary, but I put in 135 just for giggles. And then what you do that is you either click solve for horn flare or solve for high cutoff frequency. And I usually hit the fine flare button. And look at this. You get all your parameters to go into Hornresp with, and you can just fiddle with it from there. So yeah, if you're designing one of these, go out of your way, get this spreadsheet. I think it is still available, so yes, do that. So we're going to talk about the designs I wanted to do but never implemented here. No save changes to current record. Okay, where is it here? We want tang band. This is basically... Oh, let's see here. Is this the right one? I think it's this one. This is basically the design I was thinking about doing back when I did my original tapped horn video. The one that uses the 4 5-inch drivers. I do believe. Is it? I don't know. Let me check here. I don't think it is, actually. Let me find it. Okay, here it is. Now. Yes, that's the one. 2 parallel, 2 series, 4 or 5-inch drivers total. So what we're looking for, or what we're looking at here, is basically the same compression ratio I go with on all my tapped horn designs, which is about 3:1. And let's see, I've got it modeled in 2 pi here. 2 volts, basically 1 watt. Let's see here. Let me hit the edit button so we can actually change this again. Well, actually, we'll keep it in 2 pi. Because this was basically a pro audio design I was putting together here. Oh, what am I doing? I'm losing my train of thought here. Gone off the rails it has. Okay, so here's what this one looks like in acoustical power. Or basically the frequency response. Basically, this is a more ideal horn flare than anything else I've ever designed. You can see the peak in the middle here just about touches the upper peaks here. This spike here we can kind of ignore. But yeah, this is basically 1 watt input here. You get 90 decibels thereabouts at 28 hertz or so. That's what I was kind of going for with this design. So yeah, let's give it some power. I think I had this intended for 150 watts or so. Let's see what we get. Yeah, 150 watts gets you 114.6 decibels at 28 hertz with this design. That's in half space, so basically sitting out in a driveway somewhere. Now, diaphragm displacement. Can't remember what these drivers are offhand, but 7 millimeters is probably more than enough for them. Or probably safe enough for them, I mean. So, phase response, let's look at that real quick here. Fix the delay again. And yeah, it's basically fine because I basically used the spreadsheet like I just told you to do in the first place. So yeah, that's basically what this design could do if I actually built it. Let me put it in a room here against a wall. What SPL does it come up with then? Yeah, right there, 120 decibels. So yeah, this would make a half-decent pro audio design, like maybe for small rooms or something like that. I wouldn't try to fill a concert hall with 1 of these, or 2 of these, or even 4 of these. There are better designs to do that with, but yeah. I know I can hear some of you screaming about this right now, so let's go to Wolfhorn San Andreas and talk about that monster. And we'll talk about how expensive it would be if I ever tried to build that beast. Let's see, where is it here? It's here somewhere. Okay, basically, from what you can see here, I basically got 2 models done on it, and basically stopped there because I knew it was going to be way too expensive to ever do. So, I'll go with the newest one here. Okay, what we have here is the usual 3:1 compression ratio. Because all of a sudden we're talking about sundown 15-inch ZV3 drivers, which are 15-inch. And I did not want to tear those things apart if I ever built one. Because those were hideously expensive back in the day. I haven't modeled any sundown drivers newer than this in 15-inch, so don't ask me about them. I don't know. I would have to basically go through all this process one more time just to figure out what's good with them or what's bad with them or not. But anyhow, I've got this modeled as quarter space here. 155 volts, so this is 3,000 watts. And it'll take every bit of it. This design is power limited, not excursion limited. So, Yeah, this is a 14 hertz design, and I don't know if you're getting excited, but I sure am just talking about this thing. Let's calculate it. Look at this. 134 decibels at 14 hertz, 1 meter. And this is quarter space against one wall. Let's see what it does in 8th space loading like it would be if it were sitting in my home theater. 3,000 watts. Now we're talking 139.9 decibels. Down here, 136 decibels. And from my experience with these, what I can tell you is these peaks and dips sort of even out in practice. So don't worry about them. This thing will probably do 137, 138 throughout the passband easily. And up here it gets above 146. So, like I said, it is a straight up monster of a design. And diaphragm displacement, it's just fine. 32 millimeters. Those drivers were built to handle that, so that's what they can do. And yeah, basically down at your excursion minima, which is down here, 4 millimeters. And yeah, basically the driver's only moving 4 millimeters at 3,000 watts to put out 140 decibels, basically, in a corner. But I should talk about this now because it is also important. At these excursion minima, you don't want to be pumping 3,000 watts into a sine wave at 14.5 hertz here. Know why? Because the cone is barely moving. The voice coils in these drivers require cooling, and they can't cool themselves if the cone's not moving. So basically what we've got here is if you put a sine wave through this thing at 3,000 watts at 14.5 hertz, you just blew the drivers, pal. Sorry, you got to go buy more drivers. And there's another excursion minima up here. Same thing, 34.7 hertz, 3,000 watts, you just blew the driver. Same thing up here. Same thing up here. Well, not the same thing up there because you're going to be low passing up there. But yeah, be very careful when you're running sine waves or anything like that through these designs. They're not built to handle it long term. These drivers aren't. They've got to keep themselves cool. So yeah, plan on them playing music. Don't plan on them playing sine waves all day, every day, 24 hours a day. Now as for what this thing would do in a car with pressure vessel gain, this design, when we're talking about this kind of volume in 8th space already, you add pressure vessel gain to this, and you put it in a car, buddy, you just lost your windshield. Most likely. I don't know exactly how loud this thing would get in a car. I don't want to find out. I value my hearing. So yeah, that's basically that. Now let me think, is there anything I'm leaving out? I'm not sure if there is at all. But yeah, let's dismiss this now and we'll go through some build pictures of the actual horns. I already had that. What am I doing? Okay, so this is basically the home theater as it's set up right now. The original Tang band horn is up top and the SDX horn is on the bottom. Oh, I did forget something. Let's get into this real quick. We've got to talk about the new SDX10, which is basically this. I modeled it just for you guys. So this is what it comes out to. The new SDX10. Basically the same thing, except this driver is now even more suited to tapped horn use than it was before. And it's got more excursion now. So, if we go to diaphragm displacement, I've allowed it to have a little more. Let's see. So yeah, 24 millimeters I've let it have in this. I think it's excursion limited at 28 millimeters. So this is plenty. We're modeling it with about 750 watts here. Or the design, that is. That's both drivers. So yeah, once again, you've got a high pass, high pass aggressively. And this is what you get when you put 750 watts into the design with these updated drivers. And let's see, let's go 8th space just for clarity's sake, as if it were my home theater again. Okay, yeah, so 750 watts into the design with these drivers, these updated drivers. Plenty of SPL, 131 now. Ridiculous. Up to about 139 up at 62 hertz. So yeah, if you want to build this design now, basically you can with the new drivers and it'll work fine. And that is good, because the old versions are no longer available. So yeah, let's go through these build pictures now. Top horn, bottom horn, SDX horn, top horn, tang band horn. This was with those weird drivers, those 8x12s. Okay, let's go through them here. This is the standing wave correction I had with my original Pioneer receiver. PL Premium. Definitely your friend when you're building this. And I build all of these with 18mm thick plywood, birch plywood. You've got to make sure it's as void-free as possible. This is basically the stock I used here. It came from Windsor Plywood, Medicine Hat. I can't remember what each sheet cost me, but it was not cheap. Because, like I said, void-free. And I think it's something like 12 layers or something like that. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At least 11 layers there. And that's me. I am 6'5", so yeah, these are monsters. And a bunch of videos here. This is the little platform I built for actually cutting the panels for these things. Or this is actually for the SDX horn by itself. Basically, I had to do this outside on the deck because there's just no room to do it anywhere else in this house. Had to build this platform out of 2x4s. And here's the bracing I used. I used this cheap brace from Home Hardware that joins in the middle for long panels. And what I had to do is I had to brace it in the middle so it wouldn't bend. Then I just had to go right across there with my circular saw and just do it all in one cut. That was fun. Not sure what I was doing here. Probably messing up the cut or something like that. Or no, I know what it is. I was building a guide for the saw, an extra saw guide. Basically doing a rough cut and then coming back along and doing a straighter cut. There's the plywood blade I used. Some of the supplies I used to do the job. Tons of number 8 1.5 screws, because that's what I used for bracing the panels. These brackets are for, well, we'll talk about that in a minute. So yeah, that's exactly what I was doing there. I was building another saw guide, because I didn't like that metal one. So we've got a sheet of plywood there ready to go. Cutting some of the panels with my clamping saw guide I use. This is only good for panels up to maybe 48 inches. So limited usefulness when it comes to a gigantic tapped horns like this. Panel number 6 going together. Basically what I did was I got my cut list together after folding, and I haven't even talked about folding yet. That's the worst part of it. We'll get to that in a second or 5. If you want to dip out now, you can. What can I say? Lots of info dumping going on. Basically, this is the enclosure as assembled. Driver's getting ready to go in. I've got this duct seal putty here. This was important. This is how you seal off your drivers from the rest of the enclosure. You cannot have any air leaks at all. Let's see, where are we here? And as you can see, I put the duct seal even around the Nutrix Speak-On terminal cups. Again, you can't have any air leaks. Here's some of the wiring here, and handy tip for you guys now, do not use these cable clamps. They do not hold up. When these things start cranking and putting out the decibels, they will rip these things right off the side. Basically what I had to do is I had to go and get the ones that glue and screw on, and then use zip ties around them. And those are holding up, fortunately. Anyhow, we've got one driver in, getting ready to wire up the second one. There's the second one there. And like I said, these just do not hold up, these clamps. Just getting her ready for testing in this picture. Video, video, video. Damage done by the both of these tapped horns. They will break your room if you're not careful. I'm not kidding you. That's what 126 decibels at listening position does. And these horns will do it. Enough with the videos. Okay, here we go. These are all the panels as cut, basically. They're all numbered, ready to go together. I'm not exactly sure what I was doing here, probably measuring. Certainly I was done cutting at this point. I used these weights here to hold down some of the panels to get the PL Premium to set up. This is the driver baffle being assembled. This was just a test fit to see if the diaphragm would clear the uneven cuts I made, because I didn't have any way of doing this better. Some of the panels are in here. Basically what I did was this little SketchUp diagram here. I basically used all the measurements off that, translated them to the full-size version, and just sort of measured my way along, and every so often I'd get panels in like this after PL premiuming them down, and then I would go underneath and go up from the bottom and just drive screws in. It's basically the only way to do something this size. Now this baffle, important. This is why I had those 4 straight brackets. It's because in order to get this design into 3 sheets of plywood, I had to build an extension on one of the panels. Otherwise, you would need a 4th piece of plywood. So that's basically what these are. These metal brackets are holding in the this extension panel while the PL Premium in between sets up. And I think I actually left these inside the horn after it got built, and they haven't worked their way loose yet, so I'm not going to worry about it, but you really should remove these if you do something like that. Okay, this is all interior panels in place. You can see there's one here. That's sort of pushing in the throat, if you will, just to make the design work. There is a little bit of dead space there that didn't get used in the design. This was basically the only way I could build it. And this is the finished product. As you can see, I've got the whole thing up on these 2 big sawhorses here. And I basically had the drill, and I just zipped all the panels in one by one, screw by screw. And yeah, the screws are still in it now. They're being used basically as a way of holding the panels in place while the PL Premium cured. I could take them all out and it would still hold them in place, the PL Premium. That stuff never lets go. But it's just easier to leave the screws in. So there's panel number 7. I think that's actually the one that insets the horn, or insets the throat of the horn. Yes, that's what it is. You can see it right there. And I had these dowels cut. This was to make sure that the driver baffle was going in at the right exact height. That's basically all those were there for. And just more shots of the build going together here. Oh, I did remove those brackets. Good. I thought I did. I wasn't sure. Okay, now, Dynamat. Does it do any good? No, not a bit. I should have just left this alone, actually. What I did was I put this in here to try to tame the ringing a little bit that results naturally from these horn designs, and it just basically does nothing. Reason being, the wavelengths are so long in this design, it just ignores the Dynamat whatsoever, so you might as well leave it out. It does nothing. More shots of it going together here. Not sure what this video was. I think this might have been driver break-in. It doesn't matter. Yeah, that's what that was. Anyhow, we're going to go back into here and talk about the folding process, which is unbearably difficult. Oh, but before that, to start out, before you go into SketchUp or your favorite modeling program, there is a way to easily export your horn through Hornresp. You use the export here, and then you can export to a text file, and then that text file will have all the dimensions you need to come into SketchUp here and draw your initial fold. This is obviously the completed result, but what you do is you basically draw your horn in one straight line, and then you basically cut and paste and just sort of twiddle the segments around until you find something that you think is going to work. And then when you have something that you think is going to work, like this right here, you have to go back into Hornresp, use the measuring tool in SketchUp or your favorite modeling software, and just sort of measure all the segments, plug them back into Hornresp, do the whole modeling thing all over again. And if you're not content with the results, then you got to come back in here and you got to do it all over again. And you have to do that over and over until you come up with a result you're happy with. In this case, I got all the way down to fold 3L before I was happy. That took 6 months, like I said. And you're probably wondering what all these weird panels are. These light brown colored panels. Well, this is the optional bracing for this design. The SDX horn. It isn't required. It does help. So basically, if you wanted to implement bracing in the design, this is what you would do. So yeah, these colored lines here, the blue and green ones, these are the front to back bracing. So yeah, you've got these top to bottom braces and you've got the front to back braces, and this will hold it pretty much rigid, as it were. This is optional in this design, but if you ever built something like my Wolfhorn San Andreas, suddenly optional becomes mandatory. Because that design uses 15-inch drivers, and I believe I had it at 20-inch depth or something like that. You have to brace it. There's no getting around it. I think I was thinking about using 1-inch plywood for that, and using one whole sheet of 4x8 foot plywood for one side each of that design. So it probably would require 4 to 5 sheets of 1-inch thick plywood to do that design with. So yeah, now you know why I've never done that one. But yeah, this is the hard part, folding. It always is the hard part. So I try to keep it as easy as possible. So you'll notice that both of my designs look exactly like this, and all my future designs will probably look exactly like this if I ever do another one. I basically have no need to do another one at this point because the SDX horn and the Tangband horn together, they give me all the SPL I would ever need. I've had them doing up to 126 decibels at listening position, and they don't break a sweat doing that. In fact, I would estimate they're only pulling about 400 to 450 watts out of my amplifier while doing that. So yeah, basically what I could do is I could take the QSC amp out of the equation right now. I could reconfigure my drivers for 2 ohms, and I could pull out that Sony ES receiver, which is rated at 275 watts per channel into 2 ohms, and it would push these horns to room-breaking volume levels. So, yeah, I'm very, very, very happy with what I have these days. So, let me think. Did I forget anything this time? I don't know that I did. I'm kind of losing my voice here. Anyway, I think I'm going to conclude the video here. So hopefully I haven't left you leaving too many questions. If I have, like I said, put them down in the comments below and I'll try and answer them if I can. That's going to be it for today, guys. I'll see you next time. Take care.